Hi class, in this lecture here we want to begin our study of the topic of integration. And now if any of you are going to be moving on past this class to be taking Calculus 2, you're going to spend a lot of time talking about integration. Just like how we spent a lot of time in this class talking about differentiation and then the applications of differentiation, you're going to be spending a lot of time learning a lot more advanced integration methods and then a lot of the applications of integration. So these next couple lectures is just an introduction to the topic, some real basic formulas with it. One of the last things we'll talk about is something called the fundamental theorem of calculus, which will involve using integration. And the lecture today is going to be about something called an antiderivative and the indefinite integration, or the indefinite integral, and indefinite integration here. Okay, so what are we going to cover in this section? We're going to use that indefinite integral that I was talking about to find antiderivatives. And then we're going to use basic integration rules to find an antiderivative. And there is going to be a ton of rules, and you'll see in the coming slides here all the different rules. I won't even be able to go through all of them. But one thing you should do when we get to them is you should print them out and have them handy. Okay, so kind of like what is an antiderivative? So let's find a function f whose derivative is lowercase f of x is equal to 2x. So think to yourself, like what function, all right, when I take its derivative is 2x, right? Well, what if this function f is equal to x squared? And it's like, absolutely. When this function's derivative, okay, so f prime of x here, we're going to denote as lowercase f of x. I know it's going to seem a little weird, this notation. And this is indeed equal to 2x, right? So we found it, okay? And this function f here, this capital F here, this is called an antiderivative. Think about like what you're doing is you're undoing the derivative, okay? So a function capital F is an antiderivative of lowercase f on an interval I when f prime of x is equal to f of x, so capital F prime of x is equal to lowercase f of x for all x and I, okay? And this is true. You can see with this example. But what's interesting is could capital F of x also be, could it be x squared plus 5? Could it have been x squared plus 3? Could it have been x squared minus 12? You can see here that you can tack on any constant here. So the way we're going to show antiderivatives is the following way. If capital F is an antiderivative of f on an interval I, then g, so capital G is an antiderivative of f as well, lowercase f, on the interval I, if and only if g is of this form. G of x is equal to capital F of x plus c for all x and I, where c is a constant. And we call this c the constant of integration. The constant of integration. And what's going on here is like when you find an antiderivative, like we did up in the first part here, okay, and it's like, well, when I take its derivative, I get, 2x. Well, there could have been any constant, an infinite number of possible constants that could have been attached to that function. So instead of just saying, oh, the constant was 5 or the constant was 3, we just do plus c to signify, hey, could have been any constant there. Okay, so this antiderivatives, just kind of bringing it all together. Think of this as, okay, undoing the derivative. Okay, you're going to undo the derivative, all right? You're going to be like, well, this is the derivative. Well, then what was the original function here? All right, so the way we do this, okay, is we're actually going to set it up by solving a differential equation. All right, so dy dx is equal to f of x here. Like you can see here that the derivative is lowercase f of x. Well, if you divide over the differentials, right, dy is a differential, dx is a differential, you get dy is equal to f of x times dx here. And what we want to do is we want to solve this equation here. We want to just solve for y. Okay, so Okay, so we want to undo the derivative here somehow. Okay. Now the operation for finding all solutions of this equation, all right, is called antidifferentiation, or the process or the mathematical operator is called using an indefinite integral or an indefinite integration. And it is denoted by this sign here. Okay. The way I like to describe this sign is when you see a violin, this looks like the parts that are cut into the violin a little bit. That's kind of the way I like it to think about it. But this, whenever you see me write something like this, okay, sometimes I'll get a little sloppy on it. Anything like this. This is the indefinite integral. All right, the integral sign. In a later section, we'll talk about something called a definite integral. All right, and the solution to this differential equation here, okay, is denoted by this. Y is equal to, we're going to integrate f of x, okay, that's what's called the integrand. That's the function we're finding the antiderivative for. Dx here, this tells us the variable of integration. So this says integrate with respect to the x variable. This is equal to capital F of x. Okay, this is the antiderivative of f lowercase of x. Plus c, all right, because there could be any constant. So we just say plus c, the constant of integration. All right. So in this text, this notation, the integral of f of x dx is equal to capital F of x plus c, means that f is an antiderivative of f on an interval. So on any interval for this function. Okay, so solving this, okay, actually isn't that bad, and there's just going to be a lot of rules that we're gonna follow for this. Okay, so here are some basic integration rules. All right, and what I have over here, okay, is the differential form, and then we're going to use these integration formulas. So we're going to use this stuff in this section. So look, the derivative of a constant is 0. Okay, so what that means is the integral of 0, all right, is equal to a constant. The derivative of k, where k is just some constant, all right, some number, k times x, well, the derivative of that is just x. So what that means is when you integrate just a number k with respect to x, you get k times x plus your constant of integration. All right, what this rule here is saying is you can factor out a constant within a integral sign. Here, if you have the derivative with respect to x of f of x plus or minus gx, you can just take the derivative of the two terms here. And it's the same thing with an integral, right? When you're going to integrate, right, something plus or minus something else, you can just integrate them separately. Okay, and now this is the rule we're going to use the most today. All right, so look, we know when we differentiate x to the n, you bring the n down by multiplying, okay, and then you take x and you raise to the n minus 1 power. So the way it works with integration is instead of multiplying, we divide, and instead of subtracting, we add. So if you're going to integrate x to the n, okay, and this is when n is not equal to -1, so we'll talk about that case later on. With respect to the x variable, this is going to be equal to x to the n plus 1 divided by n plus 1 plus c. All right, and I'm going to do a ton of examples in this lecture of this power rule for integration, a ton. So by the end of all my examples, you'll be like, okay, Matt, I got it. All right, so have these rules very handy as you work through all your problems. And then over here we have trig, exponential, transcendental function rules. Okay, so look. The derivative of sine is cosine. That means the integral of cosine of x dx is sine of x plus c. The derivative of cosine of x is minus sine of x. Well, then if you're going to integrate just sine, all right, of x dx, you're going to get minus cosine of x plus c. And you can see all the other rules going down. Okay, I'm not going to read through them all, but you'll be able to see them here. Okay, and we'll work a bunch of examples with this. Note here, this is an important one. You'll notice that the power rule does not work when the exponent is -1. Well, in that case, when you have 1 over x and you integrate with respect to x dx, that's just the natural log, right? Because the derivative of the natural log is 1 over x. All right, we got it. All right, let's now do a bunch of examples so you can see this. I have over 10 examples of all this just so you can see how this is going to be done. Okay, so in all these examples here, what we want to do is we want to find the indefinite integral. So he'll be the first one. Let's integrate 7 with respect to x. So the integral of 7 dx here. Well, when I look back here in my rules, look, it's just a constant. Okay, 7 is just my k here. So this would just be 7 times x plus c. Yeah, and look, the way you can check your work, okay, this is really important. The way you can check your work is if you take the derivative with respect to x of your solution, you get back to the integrand right here. You get back to 7. So this totally works. All right, let's try this one. Let's find the integral of dx, or 2x, excuse me, 2 times x dx. So look, we actually started off. This was literally the first example we did. Okay? We saw that the answer here is going to be x squared plus some constant. Okay? So look, I'm going to factor out the 2. I'm going to write this as x to the 1 power dx. So then here, I'm just going to use the power rule. All right, which is the integral of x to the n dx is x to the n plus 1 divided by n plus 1. So don't forget you have this 2. And then this is x to the 1 plus 1 divided by 1 plus 1. And then don't forget you have the c. Well, 1 plus 1 is 2. Well, look, the 2's are going to cancel here. And you get exactly what we started the class with right there. Okay? So you're just going to follow the power rule. Follow the power rule here. All right, let's try a bunch more here. Let's try this one. Let's integrate x to the 5th power plus 2 dx. All right, well, if you want, you can integrate this separately. You could write this as the integral of x to the 5th dx plus the integral of 2 dx. Well, here you're just going to use the power rule, okay? This is x, you're going to take 5 plus 1 divided by 5 plus 1. And then we saw that the integral of a constant here would just be 2x. And then don't forget, whenever you complete any of these, you're just going to write that plus c there at the end. So this literally ends up just being x to the 6th over 6 plus 2x plus c. And look, if you take the derivative of this, okay, well, the 6 comes down, cancels. You just get x to the 5th plus 2, which is what we have right there. So this works. Okay, we got it. Let's try this one. Let's integrate the square root of x dx. All right, well, you might look at this and you might say, okay, well, let me go back and look at all my rules. You know, I don't see a rule for integral with the square root of x, so maybe I can't solve it. But look, what you're going to do is you're going to rewrite it. This is going to be rewritten as x to the 1/2 power dx. So now once you have it here, now you're just going to apply the power rule. So this is x to the 1/2 plus 1 divided by 1/2 plus 1 plus c. So 1/2 plus 1 gets me x to the 3/2 all over 3/2 plus c. And then this fraction comes up as its reciprocal. So this ends up being 2/3 x to the 3/2 plus c. And look, if you differentiate this, boom, you're just going to get the square root of x. Well, let's try this one. Let's integrate 1 over 2 square root of x dx. All right, well, the 1/2, the 1 over 2, I'm just going to factor out. And I'm going to rewrite this as x to the minus 1/2 dx. So look, I am just going to apply my power rule. Just apply my power rule. So this is x to the minus 1/2 plus 1 all over minus 1/2 plus 1 plus c. Minus 1/2 plus 1 gets me x to the 1/2 divided by 1/2 plus c. The 1/2 and 1/2 will cancel, or you could think of the 1/2 coming up as 2 over 1 and then canceling out. So you just get x to the 1/2 plus c, which is the same thing as the square root of x plus c. So again, for here it was just whenever you can, just follow the power rule, okay? All right. Let's try a couple more. Let's find this one. Let's find the integral of x to the 4th minus 3x squared plus 5 all over x to the 4th dx. Okay, how would I even begin to solve this? So what you're going to do here is you're going to break this up, okay? Watch what happens when I do. I'm going to write this as x to the 4th over x to the 4th minus 3/2, or excuse me, minus 3x squared over x to the 4th, not 3/2, sorry about that, plus 5 over x to the 4th dx. Now watch what happens when I simplify here. X to the 4th over x to the 4th is 1 minus x squared divided by x to the 4th gets me 3x to the minus 2. And this I'm just going to write as plus 5 x to the minus 4 dx. Now you're ready to solve this. I'm going to move this over here. This becomes the integral of a constant 1 is just 1x, or x, I'm just going to write it as 1x for now, minus 3, and then I'm going to power rule this. X to the minus 3 times x to the minus 2 plus 1 all over minus 2 plus 1 plus 5 times x to the minus 4 plus 1 all over minus 4 plus 1, and then plus c. Well, look here. This is, I'm just going to write as x. Minus 2 plus 1 gets me minus 1, so minus minus becomes plus 3 x to the minus 1 power. Plus, and then 5 over minus 3, so this actually just becomes minus 5/3 over x to the minus 3 plus c. And then we can even write this as x plus 3 over x minus 5 over 3x cubed plus c. And there we go. We got it. Let's try this one right here. Let's do a trig one now. Let's find the integral of 5 cosine of x plus 4 sine of x dx. Well, look here. The 5 in front is just a constant, okay? So you're just going to go, okay, well, what is the integral of cosine of x? You're just going to go back and go, look, the integral of cosine of x is sine of x, and the integral of sine of x is minus cosine of x. So this becomes 5, and then the integral of cosine is sine of x, plus 4, and then the integral of sine is minus cosine of x plus c. So then I'm just going to write this as 5 sine of x minus 4 cosine of x plus c. And look, if you take the derivative of this, you get 5 cosine of x plus 4 sine of x, and that's it. All right, let's do a few more trig ones here. I'm going to actually, even on this next one, I'm going to mix up the variable here. So let's integrate tangent squared of y plus 1 dy. Now, it doesn't matter if it's dy or dx here. It doesn't. It's still the same exact process. Okay, so maybe the first thing you're going to do is you're going to go, okay, so I see tangent. All right, tangent. What is tangent squared integrate as? And if you look here, there's no tangent squared, okay? No tangent squared. So what you're going to do when you have one of these trig ones is you just have to recall a trig identity. Recall that tangent squared of y plus 1 is equal to secant squared of y. So this is the same thing as the integral of secant squared of y dy. Well, let's go back. Look, the integral of secant squared is just tangent. So this just becomes tangent of y plus c. So don't be afraid, when you see these to go, all right, well, maybe I'm going to need a trig identity for some of these. All right, let's try this one. Let's integrate cosecant squared of x minus 5 e to the x dx. All right, so let's just take it term by term. Cosecant squared of x. Cosecant squared of x right here, that's going to integrate as negative cotangent of x. So this first part here is negative cotangent of x minus, and then the 5 here. Well, then what is the integral of e to the x? Well, look, the integral of e to the x is just e to the x, because the derivative of e to the x is just e to the x. And then my plus c for the constant of integration. All right, let's try this one. Let's look at the integral of 5x minus 2 raised to the x power dx. All right, well, this one here, this is just 5 times x to the 1 plus 1 divided by 1 plus 1 minus, now 2 to the x power. That's the integral of a to the x right here. So that's going to integrate as 1 over the natural log of a times a to the x. Well, here my a is 2, so this integrates as 1 over the natural log of 2 times 2 to the x plus c. And then, well, look, let me just clean this up. 1 plus 1 is 2, so this becomes 5 halves x squared. I'm going to write this as 2x, 2 to the x, divided by the natural log of 2 plus c. All right, so hopefully you're seeing the pattern here, right? It's recognized, if it's not the power rule, use one of the other formulas that are listed there. All right, let's try this one here. Let's integrate x minus 5 over x dx. All right, well, x, we know that x is going to integrate as x to the 1 plus 1 divided by 1 plus 1 minus. Now look, the 5 here doesn't matter. Okay, so I'm just going to I'll even write it out over here. So then what does 1 over x integrate as? Well, look, whenever you have 1 over x, if there was a 5 here, it would just be 5 in the front here, okay? Whenever you integrate 1 over x, It's just the natural log of the absolute value of x. You have to write the absolute value, right? Because natural log is not defined for negative numbers. So it's the natural log of the absolute value of x plus c. So whenever you get that 1 over x part here, natural log. So this just ends up being 1/2 x squared minus 5 times the natural log of the absolute value of x plus c. All right, let's look at this one. Let's integrate 4 over x minus cosecant of x cotangent of x dx. All right, well, again, this just ends up integrating. So this is 4 times 1 over x. So this is going to integrate as 4 times the natural log of the absolute value of x. All right, then minus, well, now let's go see what cosecant x cotangent x integrates as. Well, right here, cosecant of x cotangent of x integrates as negative cosecant of x. And then your last step, you can go negative, negative, becomes a positive. And just like that. All right, class. So what you can see here is I could keep doing examples till I'm blue till we're all blue in the face here. But you can kind of just see it's really just about following the formula, right? Follow those formulas. Recognize when you can use the power rule here, and we're going to keep doing these integrals in the coming lectures. And you'll also get a chance to practice it as you work on your homework.